The topic for this video is still strings. We are going to talk about very basic property of strings. We're going to talk about doing some input-output operation with strings, and then we're going to try to wrap this up in a little example. Okay, a little example that is going to try to push it as far as I want you to be able to push it in this course, which is dynamically allocating an array, and each element of this array is going to be itself a dynamically allocated string of varying size. Okay, so we are going to kind of try to conclude the video with this example. So let's jump in directly into some code. Okay, what I'm going to show you here is first the declaration of strings. So it's nothing new really, but I want to go over a few details, additional details about what happens when you declare strings a certain way versus another way. Okay, so what are those ways and other ways that I'm talking about? These are declaring strings, for example, string S1 as an array of character. So if I want to declare it as an array of character, I can initialize it using the block initialization syntax for arrays. Okay, and I'm going to say, for example, that this particular string is made of the letter H-E-L-L-O. And because I'm treating my strings as an array of character, I have to add at the end of my message that special character \0. That means end of string marker. Okay, so there you go. I have a string S1 that is declared here. I'm going to start compiling the stuff often to make sure I don't introduce a syntax error. If I run it, nothing happened, but I'm going to change that. I'm going to do a printf, and I'm going to say I want to display the content of this string. Go to the next line, S1, and there you go. I have a string that is recognized now by printf. I can display it on the screen, do all sorts of things. And then what? Well, the second version of the syntax for declaring strings that we have been using actually since the beginning of the course, but there was no explanation really about what was happening. So now that we have covered pointers, you have a better idea of what this notation is going to imply. And now I'm going to put another layer on top of that, and we're going to discuss some of the limitation when you declare strings with pointers. So here we are, S2 is a string declared as a pointer on char, and the way that we have to initialize those is really convenient. We use a double quote for syntax that corresponds to string literal. So hello is a string literal, the value of the string is literally put into the code, and we say that S2 needs to point to that string literal. So let me pause a minute here because I need to grab a whiteboard, and we're going to discuss a little bit the difference in representation in memory of both of those things. So here's the whiteboard. So in the first case, S1, okay, we have a variable S1 that is standalone like this. And that variable, sorry, that name S1, we don't have a variable S1 that is standalone, sorry. I'm jumping directly to S2 here. With S1, we have actually the label S1 that corresponds to a zone of memory. This is the address of the first element of an array of character. So here's the character H, followed by a E, followed by a L, followed by another L, followed by O, followed by the end of string marker, which I'm going to denote just with by crossing this element of the array. So this is S1. S2 is a pointer. So this is a variable in and by itself that contains a memory address. That memory address is the memory address of the character H. That is, no, I'd better do my array first, otherwise I'm going to make a mess. There we go. H, that is the first character of a string, literal, that reads hello. And again, \0 at the end. So S2 points to the memory address where the H is located. And it looks like it's the same thing. S1 is the address of the H. S2 is a variable that contains the address of the H? Well, yeah, there is a level of interaction. We already talked about that when we talked about pointers, okay? Pointers, arrays of int, for example, and dynamical allocation of arrays of integers, for example. So the same applies to arrays of characters, no problem. But there's another thing that happens here with string literal. This here currently is stored on the stack. This here is stored also on the stack. S1 is a local variable of the main method, of the main function, sorry. S2 is a local variable of the main function as well. What about this? Well, we have a right to expect, that this would be also stored on the stack, but it's not. And that's going to make a big difference. This is stored actually in a different segment of the memory space, of the address space of the process that is running. And this is actually read-only memory. That means that for all intent and purposes, this string here is what we call immutable, cannot be mutated, cannot be changed, okay, that's the terminology. Whereas this string here, which is just an array of character, is perfectly mutable. Mutable meaning, again, changeable. Let's take a look at code and let's illustrate exactly what that means. So I'm going to display both strings. I'm going to display S1. So I'm going to say S1 is, there we go, a tabulation. Then I'm going to go to the next line and I'm going to say S2 is a tabulation, %s, and then go to the next line. And I'm going to display S1 and S2. So right now, no differences, right? I have S1, S2, they are declared differently, but when I pass them as argument to printf, S1 corresponds to the address of the letter H for the first string, the string that is represented as a character, an array of character, and S2 is a pointer, and the value of that pointer, which is what we're going to pass as argument to printf, is actually, guess what, the address of the H for the second string, which is actually a string literal. So as long as I'm just accessing those strings to read them, to display them, and stuff like that, no difference whatsoever. But now I want to modify those strings. So I'm going to start with S1. The easiest way to modify, for example, to turn that L, that is a lowercase l, into an uppercase L, I'm going to say this is index 0, 1, 2. So I want to modify the element at index 2 in that character array. And I'm going to say that I want it to be an uppercase L. If I do this, and I display again, I'm going to grab this and cut and paste it, and I display again both strings, you're going to see that I'm changing actually the string itself. Here we are. S1 is hello here, and then after the modification, S1 has an uppercase L for the first L of hello. All right. So I can use this notation, and then as we discussed already with pointers and arrays and their relation with one another, I could also say I want to take the address S1. So S1 again is like a constant pointer that represents the address of the first element of the array, right? So I want to take this address. I want to add 3 as an offset to that address. So it's not going to be 3 bytes or 3 bits or 3 whatever in memory. This is going to be 3 times a number of bytes that is 3 times the size of an element in the array, so 3 times the size of a char. We already covered that. And I'm going to dereference whatever I find at this address, which is going to be the 4th element of my array, and say that I want to assign a new value, which is uppercase L. So what I'm doing here is I'm trying to change the second L of hello, again from lowercase to uppercase. Let's save it, give it a spin. There we go. And now you can see that in S1, I changed successfully using 2 different notation, using the array notation with square bracket and the pointer arithmetic notation with the dereference operator, the star, and then an expression that represents the memory where we start and the offset from that starting address, okay? I've been using those 2 notations to change actually element inside of my string, characters inside of my string. Well, I'm going to try to do the same thing with S2. So I'm going to say, I'm going to be lazy, and I'm going to cut and paste this. Here we are. And I'm going to say now I want to do S2 index 2 equal L, and S2 dereference equal L. Okay, those two notations should work because internally, if I bring back that little diagram that we have, internally is a string is really a sequence of character in memory. So you could say an array of character that is terminated as a convention by a character, special character that is the \0 character, the null character, it's also called, or the character of index 0 in the ASCII table. Okay, so that null character here is what marks the end of the string in memory. So all I have to do is to locate a string is to take the address of the first element, and I know that I'm going to find all the letters, and I know where to stop when I encounter that \0. Okay, so all of this is kind of review stuff. We already mentioned all of that. So because of that property, whether you give me the address of the first element with S1 directly, or you give me a variable S2 that contains the address of the first element, once we get over that difference, I should be able to use pointer arithmetic or array index notation. So that's the theory. And I'm going to save this. We're going to compile it again, run it again. And this is what happens. So the first printf works. Okay. The first assignment here, line 9, line 10, we already tested those. These work so far so good. No problem. And then when we try to modify here one of the character inside string S2, so this L or this L, then this is where we get a segmentation fault. Okay, so segmentation fault means that your process is executing an instruction, your program is executing an instruction that is trying to access a certain memory address. But that memory address is off limit. It's off limit because it's not mapped into the address space of the process. This is something you are going to study in more detail when you take the operating system class, okay? Or simply it's the address 0. The address 0, every time you try to access address 0, you are going to create a segmentation fault, okay? This is why we say that when you dereference a null pointer, you get a segmentation fault, you crash your program. Or you are trying to access a memory address that is supposed to be read-only, and you're trying to write something there. Well, that's the last scenario that is happening right now, okay? That, like I said at the beginning, okay, that string here is stored actually in a read-only portion of the process address space. Why? Because it has been specified as a string literal, okay? So I didn't specify it as an array of characters. I didn't specify it by dynamically allocating the string as we have done in the previous video. I just specified it as a string literal. All string literals are read-only immutable. So when I try to modify this, again, I'm accessing a certain memory address, trying to write there, but I am not allowed to write at that specific memory address. Boom, the program crashes. Okay? So that's the first thing that I wanted to really draw your attention to. There are a lot of similarities between arrays of characters, between strings that are defined as pointer and dynamically allocated, strings that are defined as pointer and that are initialized, using a string literal notation. A lot of stuff is similar, true. But you have to watch out for those little subtle details because these are the ones that are going to cause bugs if you misunderstand them. All right? So that's the first thing I wanted to show you. So I'm going to comment out those lines. And now what we're going to talk about, kind of a side property of the way strings are working. Let me get the whiteboard again to show you exactly what I mean with a little diagram visually. It's easier. What if I had a third pointer here? Well, a second pointer technically. Named S3, that is a pointer on char, so a pointer on string, right? And I made it point to this element right here. So whatever address here, let's call it beta, okay? This L character starts at, I put the value beta, and now I have a pointer that points to this. Well, S2 points to the H. S2 is a string. And when I try to printf S2, the string referred to by S2, I look at where S2 point, and then I read every character until I encounter the end of string marker. Okay, what happened with S3? Well, the same thing. S3 is also a string. It's a string because it's the address of an element, that's L, and when I want to display the string referred to by S3, I can display the L, then the next L, then the O, and then I find an end of string marker. So it's a well-formed string in memory. The thing is that S2 and S3 are not two separate independent strings. In memory, I have only one string, really, hello, with the end of string marker at the end. And what I do is I use multiple pointers that are pointing at different characters in that string, and they allow me to, this way, do a quick and dirty definition of a substring. Okay, a substring that's not really a substring that could start anywhere and stop anywhere. It's a substring that could start anywhere in the original string. It could start at any letter, and it's going to end at the end of the original substring. Okay, so you're going to see why this is important, because we are going to, as we go through the reading assignment, the material from the reading assignment, there are some functions in the string library that are actually using this property. And more specifically, it's going to be the case when we study the function str2k tokenizer, strtok, that is actually using that trick. And it's really important that you know that it's using that trick. Otherwise, as I'm going to illustrate in one of the upcoming videos, it would lead to some very weird behavior in your code. Okay, so let's leave that for like a little later. But right now, the focus for us is, what if I have a pointer S3, so char star S3, okay? And I'm going to say that S3 is equal to, for example, S1 index, not S1 index 2, is going to be equal to S1 plus 2. So the address at which the H start for the string here, plus 2, so 0, 1, 2. There we go. This is going to be the address of this element. And now I have a pointer S3 that is pointing right in the middle of my original string. But if I pass it to a printf statement, for example, here I'm going to do printf S1, S2, and S3, since I have S3 now, and I'm going to add a line to printf the information about S3. Here we are. So now I'm going to be able to use S3 as meaning I want to display every character in the original substring starting in the middle, starting with the L right there in the middle up to the end of the string. So this is going to really correspond to the diagram that I have actually in the whiteboard, right? So let's compile this. Let's try to run it. So what do we have? The first printf here is generating the first two lines. So hello and hello, nothing changed. Then S1, yes, S1 has been modified. We changed the lowercase l into an uppercase L. Here we are. S2 has not been modified. Remember, I tried to modify it and I failed tremendously, so I gave up on that. So S2 is not modified because it's not modifiable, pretty much. And then when I try to display S3, so S3 points in the middle of S1, but remember S1 has been modified. The L's, which were lowercase, are now uppercase. So when I try to display the string S3, I get the address of the first uppercase L, I display it. I look for the next character, an uppercase L again, I display it. I find a O, and then I find end of string marker, and I know that I need to stop displaying my string. Okay, so printf can handle S3 as being pretty much a substring inside S1 that starts in the middle and ends wherever S1 was ending originally as well. So it's not like a way to get like any arbitrary substring that you want, but it's still a very economical way to get a quick and dirty version of a substring that is very good when you just want to know what's left in my string after, for example, the initial HE part of the message. Okay, so hello, HE, what's left after, I can put a pointer there, and I have the rest of my string. Then what's left after the two L's, I can have a pointer S4 that's going to point to the address of the character O in the string hello, and I'll be all set. Okay, and this is exactly what str2k is str-talk, I always pronounce it weird, str-talk is going to do when we study that function from the standard string library. All right, so now that we have discussed about this little side effect of the structure of string that allows us to have pointers like right in the middle of the string, we are going to go back to something that is much more general, which is input-output using strings. So input-output using strings, we have done already input-output using strings. Okay, we have used scanf. So generally, what I suggested that you do is you create a variable called buffer, whatever you want to call it. You make it arbitrarily large. Okay, so for example, for 100 characters. And then you're going to say, so first let's tell the user printf enter a string. Okay, and then we are going to do scanf. So most of this is a review, but I'm going to particularly focus on one thing that I kind of swept under the rug in the previous videos and modules. But now we're going to discuss it in detail. Okay, so first you tell the user enter a string, then you do a scanf %s, and you say I want to store whatever the user types in the buffer, and then you can say printf you typed, and then we're going to follow that by whatever we read. Okay, so several things here. First thing, let's make sure that it compiles. That's always a good start, right? So there we go, compiles and run, enter a string hello, and then you typed hello. Okay, so I'm going to comment this out here because we really don't need it anymore, and it's going to prevent me from having a ton of garbage on the screen when I want to really show you only the last thing that we added to the code. Okay, here we are. So we have a little program here that reads a string, stores it in a buffer, okay, and then display it again. First thing I want to draw your attention to, this is a potential for security vulnerability. Okay, that %s here, don't do that. Don't do that because if I say, for example, my buffer is only large enough to accommodate 5 characters, okay? If I write the code like this with a %s in the scanf to read from the user directly, it's going to compile, it's going to run, and if I enter hi, well, it works without any problem. What if I enter, well, there you go, I cannot stop typing? Well, nothing prevents me from doing that. But the problem with this is that my input is longer than the 5 characters that I'm able to store safely inside my buffer. Okay? Fortunately, a recent version of the compiler are going to generate code that at runtime is going to detect that there is a possible problem, a possible security vulnerability, and crash the application. So it's not fun that the application is crashing, but it's much better to have the application crash and terminate than allowing somebody to inject more data in a buffer that was meant to hold only 5 characters. So I'll refer you in the extra material section of the module to a link to a buffer overflow for those of you who are curious about security, so that you can learn a little bit more about that. I'm not going to say more about it in the lecture, but suffice to say that this is actually the basis of a lot of exploit, okay, or has been the basis historically of a lot of exploit. Being able to inject more data to a program that is reading some data from the user, not checking how much data is coming in, and then trying to store that into a limited size container, like for example our buffer that can accommodate only 5 characters. So anything besides the 5 characters is written in memory, but it's written past the end of buffer, so it could overwrite over things that are in memory at those addresses, right? So this is the issue here, the whole issue. So fortunately, we have a way to fix that. For example, you can use the syntax of scanf to say 5s, so percent a number s, and it's going to limit actually how much you can read. And it's not really how much you can type, okay? It's just that if you type more than 5, scanf is just going to take the first 5 characters, okay? So just make sure that you put a number here that correspond to the size of your buffer. For example, if I want to allow up to 5 characters to be read, then I should have a buffer of size 6, okay? 1 additional character. Why? For the end of string marker. Always think about adding 1 for the end of string marker. So now I'm going to run this new version of the code. Compile it first, make sure it's okay, then run it again. Enter a string again. Well, there, I am not sure I can stop typing. Okay. And you typed well T. Well, 1, 2, 3, 4, 5. That's it. That's all that scanf extracted from whatever was typed. It just took the first 5 characters. So you're guaranteed that when you write your code like this, you're guaranteed that you're going to put into buffer the 5 characters that were typed. And then scanf is going to add for us nicely end of string marker. And so that's going to be a 6 character here in the string buffer. And that way we have a well-formed string that has not kind of overflowed outside the boundaries of buffer, the variable buffer in memory. So that's perfect. That's safe. Okay. So again, this is a very important principle. It's always sanitize user input. Okay. Always distrust user input. Whenever you are reading data from the console, from a file, from a command line option that is passed to your code, from a network socket, from a website, etc. Anytime you read external data, you should validate that data. You should make sure that there is no way for a ill-intentioned person to actually cause your program to misbehave because of the nature or the length or the size of the data that they are providing you with. Okay, so never assume anything. Always play it safe. Okay. All right. So that's the first thing that's very important. The second thing that I kind of swept under the rug in previous videos, but I want to focus on it right now, is what's happening with buffer here? Well, I'm just telling scanf where I want the character that I read from the keyboard to be stored, right? But I used to, at the beginning of the course, I told you, use this as a recipe. Every time you use scanner and you are reading an int, a double, a long, etc., put the name of a variable where you want to store that data as a second parameter of scanf, the second argument for scanf, and put a ampersand symbol in front of it. And I gave you that as a recipe, completely arbitrary. You know, hey, this is just the syntax of scanf. Then in the video where we started reading strings, the first video where we started to read string, quite sneakily, I just omitted that ampersand. So what's going on here? Well, now that you have been exposed to pointers, you understand a little better pointers, I can tell you the real story here. What scanf expects as its argument here is actually a pointer. It expects you to give the address where scanf is going to be able to store the data it's reading. So if it's reading an int from the user, it expects you to give the address of an int variable, so it can store inside this. Why do we need to pass as an argument the address of a variable? Very simple. I mean, we discussed that when we introduced pointer, right? Remember the swap function? If I want a method, if I want a function, sorry, inside the code for that function, if I want to be able to actually modify a variable that belongs, for example, to the main or to another function that call me, I need the address of that variable. I need a pointer on that variable. This is how we do passing parameter by reference. Okay, or if you want to be very accurate, this is how we do parameter passing by value, where the value is a spatial value, which is a memory address, which allows me to access the variable from inside the function. So here I want scanf to be able to write into the variable buffer here that I have declared in my main function. So I pass the address of buffer, but wait a minute. I don't want to write actually inside the variable buffer. I want to write inside the string. The variable buffer here, because it's an array of character, is kind of like a constant pointer that represents the address where the string starts. Well, there you go. I don't need anything else. Buffer itself gives me the address where the storage in memory of my string starts. And that's why I don't need to put an ampersand. Putting an ampersand here would mean I'm giving you the address of where the string starts. Not required. Okay? And it's particularly true when we use character arrays for strings, okay? In which case, yes, the name of the character array is actually the address where the string starts, so we can just use it like that, okay? All right, so this is, again, a little detail, as the devil is really in the detail, okay? Everything is important here, but that's also one of those things that you need to keep in mind at all time. Otherwise, it's going to introduce some nasty little bugs. All right, last thing that I want to discuss, and then we're going to wrap it up with an example. Last thing I want to discuss is, what am I reading here? So let's forget about that 5s, and let's make it like 100 or 99s, and let's make this 100. I'm making it bigger because now I want to read a sentence, okay? So enter I'm going to be more specific, a sentence. Let's compile this, run it. So the sentence is going to be, again, well, there, I am not sure I can stop typing, and hopefully this is less than 100 characters, should be. You typed well. Thank you, that's a nice compliment, but that's not what I type, right? Hello there, you typed hello. So the behavior of scanf%s, no matter how many characters you use between the percent and the s, like 99 characters in this example, right? No matter what restriction you put on the size of what's going to be read, the behavior of scanf%f is to start reading what you typed and stop the first time we encounter a separator. A separator is, for example, a white space. Okay, we have like a space here, a basic space bar, space. That's it. That's a separator. The tab, a tabulation that has been injected by typing just tab on the keyboard, right? Again, that would be considered a separator. So we're not talking about punctuation sign. We're talking about white space, tabulation, stuff like that. As soon as we encounter one, like for example, there's one between hello and there, scanf is going to say, that's it. I read pretty much the word that you were typing. So we could say that scanf%s reads one word at a time. And that's fine. Sometimes this is exactly what I want to do. Most times, I want to read actually the entire line that was typed, everything that the user typed until they hit the enter key. I want to read all of this, and I want to take it, store it somewhere, and then I want to work on it with other string manipulation function from the standard library, right? I want to work on this giant string that I read from the user and figure out, for example, where the first word starts, where it ends, and do something about it, display it or interpret it as a command or something like that, right? This is 99.9% of the time, and this is totally arbitrary percentage, of course, completely made up, but most of the time, there we go, that's better, most of the time, this is how you want to process text input from the user. You read everything they have to say up to the moment they hit enter, and then you take that giant string, you process it. But how do we get that done with scanf? Because scanf doesn't behave that way. Well, we have other options. So I'm going to comment out here scanf, and we are going to use instead fgetS. So fgetS is for get string, okay? F is for get string from a file stream. So here we are not going to use files, but we are going to still use that function, just tell it to read from the keyboard instead. So how does fgetS works? Well, fgetS is one of those functions that are explained in the reading assignment. Okay, we're going to play with it. I'm going to give you the gist of it. fgetS is going to take several arguments, 3 of them. The first one is going to be the address where you want to store the character that I read. So in our case, well, buffer. Buffer is correspond to this address, right? Then it takes another argument, which is how many characters do you want to read? 99. So instead of doing %99s here, I pass 99 as an argument to the function that's going to read data from the console for me. And then there is one more parameter, which is where do you want me to read from? Again, like I said, fgetS is, the F stands for file, right? It's meant to read from a file, or because of the way that things are implemented, reading from a network connection, a network socket can be also achieved through a file descriptor, etc. So the idea, actually, I would have to double check that. This has been so long since I opened a socket in a C language that maybe I said something stupid here. So I'll hold on to that. Don't take it with a grain of salt. I'll have to double check. But bottom line is that we are going to specify here what is called like an input stream, a file descriptor, that's going to say, you know, I want to read from the keyboard, or I want to read from this particular open file that I have, and so on and so forth. So the keyword, the value that I use for the keyboard is stdin, standard input. The standard input is a constant that allows me to tell fgetS, it has more use than that, but in this case, it allows me to specify to fgetS that I want it to start reading data, not from a file that I have created and opened on the file system, for example, but from the console and from the keyboard itself. All right. So stdin, standard input. There is also such a thing as standard output. Guess what? This is where functions like printf, for example, they display by default. Okay, they display to the standard input, which is the terminal associated to the code that you're running. So this terminal right here, for example, if I run my code from within this terminal. And there is also stderr, stderr, which is another output channel. So generally stdout and stderr end up being displayed on the console where you have been running your program, okay? But it's possible to separate them, and stderr, like the name kind of imply, is for errors, okay? So we're not going to go much more into that, but again, when you take the operating system class, you're going to talk about file descriptors and things of that nature. So this is kind of like giving you a heads up here for what's about to come next. But for us, we're just going to use in the context of fgetS, stdin to say I want to read from the keyboard. So, all right, I'm set up here with this. What's going to happen when I compile this and run it? Enter a sentence. Okay, now I am trying again. And there we go. Okay, now I'm trying again. Everything was read. There's one more thing. We're not done yet. There's one more thing. What is this? This blank space here, okay? I used to display back what was typed, and there was no blank line. So this is caused by the fact that when I typed my message, I typed O, K, space, N-O-W, space, I, etc., blah, 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 enter. When I hit the enter key, a special character \n was actually put into the input buffer of the operating system. When fgetS was reading everything I typed, it read everything I typed, including that \n. And once it found the \n, it said, okay, that was an entire line, so that's it. That's all I have to read. It took all of those characters, including the \n. It added a \0 at the end to mark the end of the string, and that's the string that fgetS stored as the address specified by buffer in my example. So when I try to display what is located at buffer, it finds the O, followed by the K, followed by a space, followed by the N, the O, the W, etc., blah, 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 blah. And after this N, the N at the end of again, there is one more character, \n, which is a return, go to the next line character. So when I display this with printf, I display the O, the K, the space, the N, the O, the W, the space, etc., blah, 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 up to that N here. And then I display one more character, which is \n. And this is how you display \n. You go to the next line in your terminal. Okay, we have been using \n all the time here, exactly for that purpose, okay, to space out things, etc. So how do I get rid of that? I don't want that. I don't want that \n at the end. I want my string to not have this \n at the end. So there is a basic way that we are going to cover in this course to get rid of this, is when you read something like that with fgetS, you know that you are going to have actually that extra \n. Well, you should get rid of it. Okay? So the way to get rid of it is buffer index the length of the buffer. So I'm going to use the strlen function that we are going to talk a little bit more about in one of the next video, okay? But it measures the length of a string, the number of characters in the string, not counting the \0. So I'm going to say, give me the length of buffer. Okay, so it's going to tell me how many characters are in buffer. I'm going to use the length -1 as the index of the last character. And sorry, not the last character, but the before the last character. And I'm going to assign this to \0. So what I'm doing here is, if we take a look in memory, okay, what's happening in memory, let me clear up a little bit of some space here real quick. This is a particularly inefficient eraser here. Okay, no matter. Let's just deal with it for now. A few more seconds and we'll be all set. And then before the next video, I'll make sure to set the eraser so that it's a little bit more efficient. All right, so back to what we were talking about here. I have this string in the memory, okay? H, E, L, L, O, for example, not a 0, sorry, for alphabet. So this is, for example, what I typed, all right? And then at the end here, I have the \n. And then the \0 that was added by fgetS when it processed the string, actually. So what I want to do here is I want to replace this guy by \0. So there are going to be two \0s in memory. Does it matter? Well, yeah, it's a waste of maybe a few bytes, okay? 1 byte, depending on how much bytes you use to store your char. I think it's still 1 byte. But beside this, no, it doesn't matter, because when you give me, for example, when you say, hey, this is a string S1, so here's the address of the H, okay, display that on the screen. I'm going to display the H, the E, the L, the O, and then if I encounter \0, I know my string is over. So by overriding this \n by \0, I didn't really shorten the string in the sense of using less memory, but I shortened the string in the sense that I'm going to stop considering my string, at that position instead of one position later after taking into consideration the \n. So that's exactly what I want to do. What would be strlen buffer in this case? H, E, L, L, O, \n. Okay, these are all the characters but the \0. So 1, 2, 3, 4, 5, 6. 6 minus 1, that gives me 5. So let's see, index 0, index 1, 2, 3, 4, and 5. So this is why I have on line 21 buffer at index strlen buffer -1 equal character \0. All right, but can I do that like this, brutally, like without checking anything first? No, there are some situations that are going to be a problem. First, I should make sure that buffer, the character at this particular index in the buffer is a \n. I don't want to insert a \0 if for whatever reason the \n was not included. That's not going to happen when I type stuff in the console, but that might happen when I read stuff, for example, from a file. So that means that I want to say something in the lines of, I'm going to do this if buffer strlen of buffer -1, all right, is, and that's going to be equal to \n. If it is equal to \n, then yes, by all means, replace it by \0. And this is getting a little long to write, so I'm going to declare int len equal strlen of buffer. All right, and then I'm going to replace this by len -1, and this similarly by len -1. We'll simplify a little my code. I'm going to make it a lot more readable. What else can happen? Well, if I don't enter anything for whatever reason, then I should not actually even try to replace anything. So if my string is of length 0, I don't do anything. So I'm going to require that the length is greater than 0, and buffer len -1 is equal to \n to do this substitution. Let's make sure that this compiles. Let's go back here. Here we go. Little problem here. What happened? strlen, yes, of course. So I have to include string.h. Okay, it's even recommended here. There we go. String.h, save this. Compile. Syntax error here on our if statement. Let me see. Yes, semicolon missing here. Nothing big. Let's go back. Compile again. Less value required. This is an assignment here, but I forgot my square bracket. So yeah, there were a lot of little typos here. Not paying attention. CCC live coding. Let's see. There we go. And then out. Enter a sentence. Hello there, everyone. Hello there, everyone. Okay. So that's pretty much what I wanted to cover, the basic stuff I wanted to cover. Now, to wrap it in a bigger example, I would say, I'm going to save that for the next video. We're going to wrap it up here because the video is getting long already. And next video, I will actually just focus on illustrating in a more complex, slightly more complex example, what we can do with dynamic allocation and strings. Okay, as always, thank you for your attention, and I'll see you right in a few minutes in the next video.